Hello, I'm Chen Qian, a PhD candidate from Tsinghua University. Today, I'd like to give you a report on our recent work published in CAiSE 20. An approach for process model extraction by multi-grained text classification. The work was jointly finished by Tsinghua University and Penn State University. The widespread adoption of conversational agents such as Alexa, Siri and Google Home demonstrates the natural demand for such assistive agents. To go beyond supporting the simplistic queries such as "what should I do next?" these agents need domain-specific procedural knowledge. Procedural knowledge, also called how-to-do-it knowledge, is the knowledge related to the execution of a series of interrelated tasks. A major source of procedural knowledge is contained in natural textual instructions, such as cooking recipes and maintenance manuals. While it is possible to manually understand, extract and reuse such knowledge from texts, ultimately that is a very labor-intensive option. To facilitate reuse and repurpose of procedural knowledge, process model extraction, PME, is emerging to automatically extract underlying process models from process texts. As this figure illustrates, PME extracts the main actions, nodes, and their ordering relations, sequence flows, expressed in the cooking recipe as a process model. Several language rule-based methods have been originally applied to process extraction. Most of this type of work introduced an extraction pipeline, using NLP tools to automatically extract structured procedures from instructions. Along this line, pattern matching-based methods designed various language patterns, considering basic language patterns, syntactic tree and anaphora resolution. Recently, some knowledge-based methods have been applied to this problem and they were shown to perform well. However, they also require a large quantity of cognition-level knowledge, which would be time-consuming and labor-intensive to build. There also exist some machine learning-based studies which incorporated traditional machine learning techniques into process extraction, such as support vector machine and conditional random field. However, PME is still challenging as it requires agents to understand complex descriptions of actions and involves multi-grained information mining. For example, to extract the whole process model, the process extractor has to recognize whether a sentence is describing an action, which is sentence-level information, and who does what in a sentence describing an action, which is word-level information. Traditional methods suffer from weak generalizability when applied in open domain or open topic scenarios since they, 1. require much large-scale and domain-specific procedural features, and 2. ignore the relations between sentence-level and word-level subtasks. In this paper, we propose a new framework to extract process models from process texts. Specifically, we first formalize the PME task into the multi-grained text classification problem, and then propose a hierarchical neural network to effectively model and extract multi-grained information without manually defined procedural features. Under this hierarchical structure, we accordingly propose the course to fine-grained learning mechanism, training multi-grained tasks and course to fine-grained order, to share the high-level knowledge for the low-level tasks. To train and evaluate our model, we construct two multi-grained datasets from two different domains and conduct extensive experiments from different dimensions. Experimental results demonstrate that our approach outperforms state-of-the-art methods with statistical significance. We first formalize the PME task into the multi-grained text classification problem. We argue that PME involves three main text classification subtasks. Sentence classification, identifying whether a sentence is describing an action or a statement. Sentence semantics recognition, recognizing the semantics of a statement sentence to control the execution of following actions. Semantic role labeling, assigning semantic roles to words or phrases in each action sentence. To mine sentence-level and word-level information effectively, we propose a deep learning-based network to model the conditional relations between three subtasks and to effectively avoid manually defining domain-specific procedural features, called multi-grained text classifier, MGTC. The figure shows the framework of our proposed approach. Specifically, we design a hierarchical structure to model the conditional relations between three subtasks and to effectively extract textual clues from different granularities. Under this framework, we accordingly propose the course to fine-grained learning mechanism, training course tasks in advance before training fine-grained tasks to share the learned high-level knowledge to the low-level tasks, which conforms with the procedure of human learning more than those methods without the consideration of different granularities. By problem mapping, the output of our model is the sentence-level and word-level labels, which could be further easily visualized as a specific, general process model or a process structure tree via intuitively creating nodes and building sequence flows from the extracted procedural knowledge. Coarse-grained learning. The goal of this phase is to learn sentence-level knowledge in advance. Embedding layer. We use word2vec to obtain word vectors, which tries to maximize classification of a word based on another word in the same sentence. More precisely, we use each current word as an input to a log linear classifier with continuous projection layer, and predict words within a certain range before and after the current word. Encoding layer. As a special type of recurrent neural network, RNN, LSTM is particularly suitable for modeling the sequential property of text data. For an input sequence, LSTM computes unit states of the network as follows and outputs contextualized word embeddings. In order to capture the information from the context both preceding and following a word, we use the bidirectional LSTM, BiLSTM, by concatenating the latent vectors from both directions to construct a bidirectional encoded vector. Convolution layer. We also employ multi-scale filters to capture local n-gram information in a sentence. Meanwhile, we use the max pooling operation to extract the most important features within each feature map. Gate attention mechanism. Since not all features contribute equally to the final task, we employ the gate attention mechanism to weight each concept information. The effect of gate attention is similar to that of feature selection. It is a soft feature selection which assigns a larger weight to a vital feature, and a small weight to a trivial feature. After concatenating all features, it is input into two fully connected multi-layer perceptron networks, MLP, to realize feature fusion. To obtain the probability distribution on each type, the softmax operation is computed. We use cross-entropy loss function to train the coarse-grained learning phase. The goal of training is to minimize the multitask loss function. Fine-grained learning. Note that the features of a small-scale classification task may be higher quality than the features of a large-scale classification task since this small-scale classification task has relatively sufficient training data. Based on that, compared with sentence-level tasks, we regard the word-level tasks as relatively large-scale classification tasks, initializing parameters of the word-level task from the sentence-level tasks and later fine-tuning it. The transfer of parameters can provide a better starting point for the latter than training from scratch using randomly initialized parameters. We extract the last hidden features in ST1 as learned sentence-level knowledge and concatenate it with word-level embedding via the gate attention mechanism. The fused representation is fed into a MLP module to perform the word-level prediction. Similarly, we use cross-entropy loss function to train the fine-grained learning phase. Since traditional methods mainly use off-the-shelf NLP tools to analyze sentences and extract corresponding information under predefined features or patterns, thus, there was no directly available multi-grained corpus for the PME task. To this end, we constructed two multi-grained PME corpora for the task of extracting process models from texts. Cooking recipes, COR, a large and diverse collection of more than 200 cooking recipes. And maintenance manuals, MAM, more than 160 maintenance descriptions. The statistics of those datasets is given in this table. Baselines. A pattern matching based method, PBSW, which uses NLP tagging tools to extract important linguistic patterns and adopts a set of heuristic anaphora resolution mechanisms to extract corresponding procedural knowledge. A language rule-based method, ARWE, which introduces a lexical approach and two further approaches based on a set of association rules created during a statistical analysis of a corpus of workflows. A traditional learning-based method, or PATM, which leverages SVM to automatically identify whether a task described in a textual description is manual or not. Implementation details. The overall results are summarized in the table. We can see that MGTC consistently outperforms all methods on all three subtasks with statistical significance. From ablation studies, we can see that the performance improves after employing the gate attention mechanism and course-defined learning. That is to say, both the gate attention mechanism and course-defined learning can improve accuracy, which shows the effectiveness of the two mechanisms. This is consistent with our intuition that training course tasks in advance before fine-grained tasks can learn to better learning procedural knowledge. The experimental results also demonstrate the disadvantages of the manual feature-based methods. First, since traditional methods employ diverse manual mechanisms or features, they suffer from the problems of poor quality and lack of adaptability. Second, by considering the long-term language changes, the framework with mixture of multi-scale filters can understand text semantics better and extract more accurate information. Third, over all subtasks and datasets, we can see that MGTC can maintain more stable results, which suggests that MGTC is more robust on different subtasks and datasets. To further investigate the independent effects of the key components in our framework, we perform ablation studies. The left figure shows the performance of those variants employing different language models. It can be observed that, when the default BERT is replaced with Elmo, Glovi or Word2Vec, the performance consistently decreases, which shows that retraining on large-scale corpora can better capture linguistic information. The middle figure shows the performance of the variants after removing n-gram filters from MGTC. It can be observed that, when n-gram filters are removed from the network, it decreases performance too. The right figure, we can observe that the performance of two-layer MLP indicates that imposing some more nonlinear neurons is useful, and that the one-layer network seems slightly weak for certain subtasks. We also conducted more experiments to further investigate the performance of traditional learning, TRAL, and our proposed course-defined learning method, C2FL. Comparing the results of TRAL and C2FL, one can see that C2FL consistently magnifies and scatters the time consumption on three subtasks. What's more, the n-fold cross-validation results show that the generalization performance of C2FL is remarkably higher than TRAL's on all subtasks. Note that many publicly available model text pairs are not considered as our datasets, because our supervised method inevitably needs much larger scale of labeled training data than traditional rule-based ones. It is also worth mentioning that although we aim to extract from general process texts, our model might suffer from low external validity. One main reason is that both recipes and manuals are rather sequential by nature, which means that we can expect a rather small number of concurrent streams of actions and complex choices. Moreover, our approach is not model-specific. For some specific models, such as PetriNet and BPMN, adding such features is a possible extension of our work. We summarize the contributions of this paper. We formalize the PME task into the multi-grained text classification problem and propose a hierarchical multi-grained network to model and extract multi-grained information. Under this structure, we accordingly propose the course-defined learning mechanism and constructed two datasets. The results demonstrate that our approach outperforms the state-of-the-art methods. Therefore, we draw two main conclusions as follows. 1. The deep learning-based process extractor can effectively capture procedural knowledge without the need for defining domain-specific procedural features, and 2. Our proposed hierarchical network and the course-defined learning mechanism can better learn the word-level clues based on pre-learned sentence-level knowledge. That's all. Thank you for your listening.